Well, thank you all for coming this morning. So Professor Ramirez is the one that conceived of Science Saturdays and ran it single-handedly for a couple years before I came on. And in classic Professor Ramirez fashion, she agreed to introduce herself this morning and tell you how fabulous she was, but of course she wouldn't tell you that. What she would say is, I'm here, I do some nice science and so forth and so on. But I want you all to know how amazing she is. So Science Saturdays-wise, this exists because of her. No one said, hey, this would be kind of cool. She said it, and she made it happen. And so you all should really... So besides doing Science Saturdays, which is easily, I think, one of the coolest things on the planet, although I am a little biased, she's also an extraordinary scientist. So Professor Ramirez started her science career at Brown University. Probably started it actually when she was 2 years old, I'm guessing, doing something cool along the way, but started at Brown University and went on to Stanford to get her PhD, and then worked at Bell Labs. And Bell Labs was probably the greatest think tank there was for doing cool materials work. And Professor Ramirez was probably one of their coolest people there that really came up with some novel materials. When I went into science, people started saying things like, there's nothing that interesting in materials. We know everything we need to know about materials at this point. And Professor Ramirez has proved people wrong. There's a lot we can learn about materials, especially if we have people like her that are incredibly creative and phenomenally wonderful. Besides being an absolutely amazing scientist, she's in fact one of the coolest people here at Yale. She's a phenomenal friend. She's a great mentor to a huge host of us here. She looks after all of us. And she's just one of the great people. So let's give her a big hand for doing this event and for being willing to lecture.
Thanks, Aaron. Thank you. I had to pay Aaron a lot of money for that, so I feel like I got my money's worth. All right, well today I'm going to talk to you about strange stuff. I'm going to talk to you a little bit about smart materials and nanotechnology. All right, so I'm a material scientist, and I think a lot about stuff. Not possessions, but just stuff. And so what I'm going to talk to you a little bit about today is smart stuff, and then I'll talk to you a little bit about very small stuff, okay? So we're going to talk about stuff today. Is that okay? All right. So let me just do a survey so that we're all on the same page. Have any of you used one of these? Okay. Any of you use one of these, a TV? Yeah? Maybe too much of it sometimes? Anybody use one of these? Oh, by the way, shut them off. How about one of these? All right. So for the most part, everybody's part of the 21st century. That's great. Well, all of these things have in common this, which is circuitry. There's resistors, transistors, capacitors, and they're all put into place into this green circuit board, and they're held into place at locations like that using a material, see, those cell phones are going off, using a material called solder. Now, although there's an L in there, and although I'm from New Jersey, I'm saying it right. It's solder, okay? In the UK, they'll say solder, but here we say solder. And solder is the material that puts into place all of these different components, all right? So let's talk a little bit more about solder. Solder is a low melting point metal. If I were to give you a piece of solder, I have a piece here, and you put it on a frying pan, not your mom's favorite frying pan, but if you heat this up on the stove, it will melt. It's a metal that will melt at such low temperatures. It's also malleable. That's just a big word for saying that it's bendable. Can you say malleable? Malleable. It means bendable. It's used to join, meaning that it's like a glue. It's a metallic glue. You can put two metals together, and you can still have electricity pass. And it's often made of two or more metals. So when you have two or more metals mixed together, that's called an alloy. Can you say alloy? Alloy. Okay. So let's go back to the survey that we just did. All of these materials, all of these instruments that we all use, all of them have circuitry inside, bonded together by this solder that holds it together. Unfortunately, all those things eventually end up here in a landfill. So in 5 to 10 years, all those items will end up in a landfill. Now, what I didn't mention is that the solder actually contains a material that we aren't too crazy about. It contains lead, all right? And lead is bad for the environment. So we have all these wonderful devices that are fantastic, but they'll eventually end up here, They'll eventually give off their lead, put it into the water table, and it will be something that we'll have to deal with because lead is toxic to us and to animals and the like. So let's talk a little bit about lead, the good, the bad, and the ugly. If you look at the periodic table, the symbol for lead is Pb. It comes from the Latin plumbum. Can you say that? Plumbum. Imagine calling lead plumbum. It's actually the same derivative that we use for the word plumber. So that might look familiar to you, plumbum. Now, the reason why that's the case is that in ancient times, plumbers used lead quite a bit. And if you look at ancient times, sort of like the Colosseum, you would see things like this. You would see coins made out of lead. And you would see right here is a duct or a pipe made out of lead in a very, very old sidewalk. And it was used to move water from one part of the city to another. And now we use lead in these electronics. So from a civilization point of view, lead has served us. But let's look at the bad and the ugly. Well, we do include it sometimes in paint, and so that's why you have to be careful never to put paint chip in your mouth. That's not good, because you could get poisoned that way. In some old cars, there's gasoline that contains some lead. Lots of old batteries contain lead as well. So for the most part, this stuff is dangerous. It's really bad. It's poisonous. So we really don't want to have lead. All right? We don't want lead. So the question I'm asking is, how do you get the lead out? Crazy picture, I know. How do we have solders that don't have lead in them? That's the question that we propose. Well, okay, so we have solder, and what it's consisting of is tin and lead. But we want to get rid of the lead, so what can we use to replace the lead? Well, other scientists have looked at different combinations of metals, different alloys, and they found that tin-silver is actually a very good combination and might be the replacement for tin-lead. However, they found out one thing, that although it can work similarly to tin-lead, it's not as strong as tin-lead. So tin-lead is bad for us, but it's really strong. Here we have something that's better for us, but it's not as strong. And sometimes that happens in science. You just have these trade-offs. So the question that we're going to ask is, if we start off with tin-silver, what can we do to strengthen it so that it has properties similar to that lead-based alloy, which is toxic? Question? I can add more, make it thicker? Yeah, that's one thing we can do. But those devices, did you see those devices, how small they are? We're actually getting smaller. Is your cell phone getting bigger or is it getting smaller? Smaller. Everything's getting smaller. So although putting a large chunk of it will work, that works in the lab, we're all going in the direction where we're getting smaller and smaller. Okay? So the issue is that tin-silver on a very small scale is still too weak compared to lead. So what can we do? So the question is, how do we strengthen materials? Well, this is what material scientists do all the time. This is my job. All right. How do you strengthen materials? And we're familiar with strengthening materials. Anybody have gold? I'm not going to take it. Anybody have gold on? All right, I have gold on. I wore it today. Gold is actually a very, very soft metal. It's a very soft metal. However, we're able to have it on our necks. We're able to have it in our ears, our teeth. Some people have it in their noses. How is it that we're able to sustain, this soft material is able to sustain such aggressive and abrasive and even nasty environments? How is it able to do that? Well, we put other metals into the gold. We put nickel and we put copper and we alloy it so that it's strong enough. So that's one thing that we can do. We can alloy material to strengthen it. Here's another way that we can strengthen a material. I have a demonstration here. I have two types of cakes here and a knife. Okay, so if I wanted to slice a pound cake, which is made out of a pound of sugar, pound of butter, pound of whatever, just a pound cake, and a fruit cake, and I were to slice them, which one would be more difficult to slice? The pound cake? All right, let's do it by a show of hands. Pound cake? Fruit cake? Okay, everybody believes me. Okay, so here's my pound cake. Look at that. That goes right through. Here's another cake with nuts in it. Taking me a little bit more effort. Now, why is that? Why is it that the fruit cake is harder, or in this case, the banana nut cake is harder? There's more stuff in it. Would everybody agree with that? There's stuff that's preventing my knife from slicing through. All right? So this process of putting stuff into stuff is actually has a technical term. It's called dispersion hardening. Dispersion means stuff. We put stuff into stuff to make it harder. Okay? Can you say dispersion hardening? That's just a technical term for stuff into stuff. All right? So we're going to put stuff into stuff to make it harder. So we had tin, silver, solder, and now we're going to put stuff into it to make it harder. So scientists have come up with a couple of ways or a couple of materials that they've put into these solders as well. What we decided we wanted to do is that we wanted to add iron. We wanted to add iron to strengthen this material. So we're putting stuff, iron, into stuff, the tin, silver, solder, to see if it will increase its strength. Okay? Is everybody on board with what we're doing? All right. Well, let's look at some data. All right? Let's see what happens when we do that. So what I have here is a bar graph, and let me explain what's going on. The taller the bar, the more strength. Okay? And so I have a couple of examples here where I have no particles, so it has no orange dots in it. I have one with 10% particles, so it has 10% orange dots in it. I have a case with 20% iron particles, so it has 20 of these orange dots, 25 orange dots. Do you see that? Okay, so the difference between no particles and 10 particles, you can see that it's significantly different, right? Would you agree? All right, so we're increasing the strength by adding stuff to stuff. So that's the first thing that we've learned. The second thing is that, well, if you keep going, you don't gain very much. You can see that 25 and 20, not that much of a difference. But when you go from nothing to something, it's a significant amount, significant change in the strength. Would you agree with that? Okay, so adding particles increases the strength. Whoops, what did I do? All right, so success. We feel pretty good about that. We did what we thought we were going to do. We increased the strength. So can I sit back and go on vacation? No. How'd you know? No, not quite there. Because it ends up that when we put those particles into the solder, that it actually became too thick. So the solder, when it was liquid, when we melted it, it poured like water. But when it had too many of these particles, it poured like pudding. Does pudding pour very well? No, not really. So it had too many particles in it. So we're not done. Although we've showed that we can increase the strength, it's still not quite there because it's too thick. So what else can we do? All right, well, let's go back to our original problem. What should we add to the silver and tin? Other people have used other materials. We're going to stick with iron because we know that it can increase the strength. But let's do this. Let's employ the fact that iron is magnetic. You might be familiar with this. So here are some pieces. Can everybody see that? All right, these are just small metallic pieces. And what I'm going to do is I've put a very strong magnet. And you see how things align and move accordingly? See that? You see how we see lines moving here? Field lines? All right, we'll get back to this in just a second. But iron is magnetic, and so we're going to employ the fact that it's magnetic. All right? So we'll get right back to that in just a second. All right, so, whoops, I want to go back. Too much technology here. All right, so the fact that it's magnetic, you may be familiar with iron, you may have seen it in things like this, but the reason why I recall that iron was magnetic is because one of my favorite toys was this. Are you familiar with this guy? You don't know Wooly Willy? I recommend you get it. So, okay, with this guy, you have iron filings, and you can move it, and now he has a little goatee, little sideburns. He's a metrosexual, so we're going to leave his hair without any hair. Okay? So, but we're just relying on the fact that iron filings can be changed or moved into position using these magnetic particles, using a magnet. Oh, he went back. Sorry about that. Okay. So let's see if we can organize. Let's go back, because this is distracting. Let's see how we can organize these particles. Okay? So let's go back to my solder. I have the tin-silver solder, which is in blue. I have the iron particles, which are indicated in orange. And let's say that we have this in its liquid form. Okay? And now we're going to put this solder in between two magnets. two magnets that are attracted to each other. Now, these magnets want to get close to each other because they're attracted to each other, but we're not going to let them. We're going to let them stay at that distance and keep the solder in between. Okay? So when we do that, these guys have a strong attraction, and everything in between is going to feel that attraction. Would you agree? All right. So what happens when we do that? Well, if I put my solder underneath, in between that two fields, the iron particles will align according to that field. Does that make sense? All right, so now we've been able to organize our iron particles. Before they were completely random, but by setting them in a magnetic field, we're able to align them along the magnetic field. Does that make sense? Okay, so here's how we're able to organize them. So let's see what kind of behavior we get in terms of their strength based on it being organized. Well, if we look at this bar chart again, once again, increased height means greater strength. And so we're going to look at the case where we have no particles. It has no orange balls in it. We have a case where we have random particles, so we have randomly oriented orange balls. And then we have organized particles where the orange balls are kind of all lined up. And you can see that the orange balls that are all lined up have a greater strength than all of them. You see that? So we've been able to modify the strength of the materials not only by putting particles into the material, putting stuff into stuff, which is dispersion hardening, right? Dispersion hardening, can you say that again? So we've done dispersion hardening, but now we're also making our particles align and increasing the strength as well. All right? So in our minds, just to show you what that looks like, if we were to use a scanning electron microscope, so these microscopes are about this big, and they cost like $500,000, and they actually allow you to look very, very small features. And here you can see an image of random particles. I'll show you what we have. We have the light gray area. That's the solder. That's the tin silver solder. And the darker regions, that's the iron. Do you see any kind of regular pattern? It's just scattered all over, right? It kind of looks like the surface of the moon, right? Just completely scattered. However, if we have a sample that was made between these two magnets, we see that we have a band. You see that's a little darker here, iron particles. There's less here, and there's more over here. So they don't completely align like they did in my image, but they kind of band together. They kind of group together, all right? And it's this material, and I show the arrows to kind of indicate where the field lines would be. So this is what the organized particles look like. And we saw that the organized particles had greater strength than those that were randomly oriented. So from our point of view, this problem is solved. All right? So we believe, I want to show you one other thing that we didn't even expect, and this happens in science too. Sometimes you want to solve a problem, and then you just try something in a lab, and you see something new. Let's look and see what happens when we heat up the solder and we place a magnet over it. Does your solder do that? So we're able to move it vertically. We moved it vertically, and we can also move it side to side. That's kind of neat, huh? All right, so what's going on? Those iron particles that are inside of the solder, they're attracted to the magnet, so they move up to the magnet, but they bring the solder along with it as well. So we're able to move things vertically. And we've actually made a whole bunch of different shapes, Y shapes, army guy shapes, using this kind of technology. Yes? That magnet's not very strong. That's a refrigerator magnet. Oh, okay. It's a refrigerator magnet, not very strong. Okay? So sometimes in science, you aim to solve a problem, and sometimes you find something else that's neat. And we're actually writing papers and patenting this because this is a way to bond things using vertical directions. What you used to do is you would have to put a layer, put solder, put another layer, put solder. Now we're saying stack up those layers, heat it up, and put a magnetic field, and the solder will go up. All right? So those are some of the neat things that we're doing with this material. So with apologies to the bionic man, we feel that we've made a material that's stronger because we've dispersion hardened it so that it will have properties equal to that of the lead-based materials. It's greener because we don't have any lead in it. And it's faster because, boy, we can do some neat things. We can move it upwards as well. All right? So mission accomplished. I'm going to change gears now. Any questions so far? Okay. I'm going to talk to you a little bit about small stuff now. I had talked a little bit about putting iron particles into solder. And those iron particles were on the scale of microns. Your hair is on the scale of microns. Your hair is about 60 microns. And the particles were about 60 microns. Now what I want to do is I want to talk about particles that are 1/10,000th that thickness. All right, so very small, on the order of nano. So let's talk a little bit about that. First, let's define this thing called nanotechnology. Nano, well, that's just a way to say very, very small, and I'll be specific about that in just a second. And technology, which is just a new pathway, a new way to create and innovate. So how small is nano? All right, what I have here is tape measure that's out to about 1 meter. You guys familiar with these things? All right, so if I have a semi-meter, that's about here, right? Now, let me get back to this guy. If I have a centimeter, you may be familiar with centimeters. Centimeters are these guys here, where it says 2, 3, 4, 5, right? And there's how many in a meter? 100, right? Now, millimeter. Millimeter are these smaller lines that are in between the centimeters, and that's 1,000, right? There's 1,000 of them in a meter. All right, then we have micro. Micro is in between the millimeter. You thought millimeter was small? We're going to do micro. Micro is in between those millimeters, all right? And there's 1,000 in there. And in between those lines, there's 1,000 more of these nano lines. Now, they're not on this thing. You can't see it. They're very, very small, okay? So it's very, very tiny, and it's very, very stuck. Very, very tiny. So if I have a meter, which is what I have here, nano is 1/1000th of this length. 1/1000th of this length. You cannot see it, all right? Just to give you another way to look at this, a sheet of paper, you have a sheet of paper in front of you? Sheet of paper is 100,000 nanometers thick, all right? A human hair, 50,000 nanometers thick, all right? I don't have as much as most of you, but it's still 50,000 nanometers thick. And your fingernail, it grows 1 nanometer per second. So by the time you say 1 Mississippi, it's grown 1 nanometer. So let's try it. 1 Mississippi, 1 nanometer is grown, okay? So let me just go back to the... So here I have an image of a human hair. This is also taken with a scanning electron microscope. And across that would be 50,000 nanometers, all right? So if you can pull out a hair, don't hurt yourself. Can you see the diameter? That diameter is this big, 50,000 nanometers across. You cannot see that. That's how tiny it is, okay? So nanotechnology is based on 2 things. This is my definition. It's small, which I tried to get across to you. It's 1/1000th of a meter, 1/1000th of a meter. But the other part is that it's curious. Curious is just a fancy way to say it acts weird, acts differently. Professors, we like to say things like we're really smart, but it's just another way to say it's weird, all right? So it's smart and it's weird. All right, I'll give you an example by what I mean by that. Let's say that I have a machine that can shrink things down to the nano size, all right? So this is not a real dog, so don't write any letters to anybody, okay? So this is a dog, and I've put it in my machine, and I'm going to shrink it. And as I shrink it, it gets smaller and smaller and smaller, turns into a cat. That's nanotechnology, all right? It was a dog at our scale, and it becomes a different animal at another scale. I'll give you an example that makes that a little bit more clear. What color is gold? Gold. Yeah, yellow, gold, all right? Let's say that I had gold particles that were 100 nanometers, all right? So I can put about 500 of them across your hair, all right? 100 nanometers, pieces of gold, nano-gold, and I were to suspend it in water. Its color is red, all right? So its properties change. So it's gone from a dog to a cat. The properties are very different. The color has changed, okay? So that's what we mean by nanotechnology. And you can continue to tailor this color, actually. Here is another material that acts like nano-gold in one way. It's called quantum dots. And if you change the size from 2 nanometers to 8 nanometers, you get this range of colors, just like a beautiful rainbow, right? So its properties also are changed by the size of the particles. Now, what's going on? There's an interaction between the light and the nanoparticle that actually causes it to excite different colors than if it were in bulk. So that's what I meant by small and curious. It just acts weird. Gold is no longer gold, it's red. That's really strange. All right? So what are some of the uses for nano-gold? This is still a technology that's in its genesis. And here are a couple of things that have kind of come up to the surface. One, it might be used for cancer treatments. It can be, which I'll show a small movie about in just a second. It can be used for environmental cleanup. The nano-gold will go to a toxin and pull it out and be a filter on a very, very small scale. And it also can be used for drug delivery. Let's say that I have a problem with my foot, and I need to take medicine for it. What I would currently do is I would take a pill. The pill would go all throughout my body, and hopefully enough of it makes it to my foot. Right? Now with nanotechnology, you can have medicines that you can take, and they will just wait until they get to the location, all right, and then release the medicines. So that's what scientists are working on right now. So let me show you a little bit of a small movie on the cancer treatments, just so you can appreciate what's going on. Everybody see?
So if you were a patient, the procedure would be pretty straightforward. First, you'd have an injection of nanoshells, and they'd circulate through the bloodstream. And over the next several hours, the patient would wait. And during that time, the nanoshells would accumulate slowly into the tumor site. And then the doctor would shine light through the skin into the tumor site. So the nanoshells will capture the light, convert the light to heat, but only sufficiently to raise the temperature of the cells until cell death is induced. The dead cells would eventually dissipate, the tumor would shrink, and the nanoshells would leave the body.
That's hot. Literally. So what's going on here? We have the nanoshells that go directly to the tumor. We shine a laser light. The laser light doesn't affect our skin. It's at a different frequency. It doesn't affect our skin, but it can directly interact with the nanoparticles and heats them up. Now, what would be the alternative if we didn't do such a technique? Well, if we had something bad in our bodies, our two options right now are surgery and chemotherapy. You might end up with a haircut like mine. So this is an alternative to that, right? This approach. So let's talk a little more positively about some things that are out there. What nanotechnology applications are out right now? Well, there's antibacterial coatings made out of silver nanoparticles, and they're being embedded in socks and in some toys. And what does that mean for us? No more smelly socks. All right? So maybe you can get a pair for Dad. All right? And also, you don't have to worry about toys being nasty after your brother or sister has coughed up on it, because you don't have to worry about that because it has these nanoparticles that are antibacterial. There's also stain-resistant pants, which is something I could definitely use. These stain-resistant pants aren't based on having nanoparticles of silver, but they're based on borrowing information from nature, specifically the lotus leaf. The lotus leaf, as you can see, has water that just kind of balls up on it, right? And if you pour water on it, the water will just spill right off. Why is that the case? Because it has a surface that looks like this. It's got whiskers that are sticking out. And it prevents water from flattening out and seeping into the pants, right? So by balling up, sort of like water that you see on the surface of a car that's really clean, that's the surface that we're creating with those pants, so that the water never gets a chance to seep in, but just rolls right off, right? So these are some of the things that already exist. And what's in the future? Well, there's definitely applications in medicine. I had talked about drug delivery. There's some applications for medical imaging. Here I have two images. This is the same patient. We're looking at an X-ray, and you can see when you use nano-gold, you get more contrast. You can see these kidneys much better than over here. So from a medical point of view, there's some applications. There's lots of environmental applications, and also, I was looking on the web, there's already health and beauty. Here's nano-gold lipstick, which is supposed to be more luminescent, and also some toothpaste, which I don't know what the cause is, but These things are out here. And also, there's always military and space applications. So, in our time together, I hope that you have learned a little bit about how we engineer materials. And I also hope that you're convinced that the next big thing is actually very, very small. In fact, it's nano. Thanks for your attention.